Okay, good morning to my colleagues here in the United States, and good evening to our colleagues and friends in India at VIT. And welcome to the second seminar as part of the joint webinar series between Binghamton University and Vellore Institute of Technology, VIT. We are very delighted to welcome all of you to the second seminar. Today, we are honored to have Professor Krishnan from the School of Mechanical Engineering at Vellore Institute of Technology. And he will talk about a novel electro-hygrothermo-mechanical approach to evaluate the static and fatigue reliability of dual and quad IC packages. Dr. Krishnan received his Ph.D. in engineering from the Department of Materials Engineering from the Indian Institute of Science in Bangalore in 1995. And has a very rich postdoctoral experience from the University of Delaware in the US and the Singapore MIT Alliance, NTU in Singapore. He is currently a professor of higher academic grade at VIT and has more than 250 publications in international journals, international conferences, and project documents. 17 books and chapters in the area of micro, nano, multi-scale, and macro composites, processing, materials characterization, electron microscopy, micro and mesomechanics, interfaces, macro mechanics, fracture and failure analysis, electronics, packaging, and FEM. So we are very honored to have Dr. Krishnan with us today to deliver his seminar. And Dr. Dean Vasudevan and I, the Dean of Mechanical Engineering at VIT, are very delighted to co-host this event and welcome you to join us today to listen to Professor Krishnan. Professor Krishnan, I will turn it over to you. And thank you, sir, for joining us.
Thank you so much, Professor Mohammed, and thanks to Professor Mark Pollix for the wonderful inauguration and the opening innings. And I hope I do my job well today. And a very good day to everybody. I hope I am clearly audible. And the title of my talk is a novel electro-hygrothermo-mechanical coupled field analysis approach to evaluate the static and fatigue reliability of dual and quad IC packages. That is dual two-sided and then four-sided IC packages. This is the work that I did with a company called SPEL. Before that, a few slides about VIT, as I have been asked to be the opening batsman from VIT, and I have this responsibility on my shoulders to tell you what VIT is all about, though some of you might be pretty comfortable with what VIT is all about. Welcome to VIT Vellore, India. This is how we look at the entrance. And our honor in 2019 was from the Government of India, as it recognized us as an institution of eminence among 10 other private institutes and 10 other public institutes. So we are now in the India's top 20 institutions, and we are also the #1 private engineering institution in India. Apart from that, we have been ranked in NIRF, then NAC a bit, NBA, IET. A bit America, they have accredited us 3 times over for 10 BTech programs and 4 BTech programs. And we also have the Excellent Enabling Research Environment Award from FICCI, and MHRD has graded us for autonomy. We have QS 5-star rating, and Web of Science has called us the most, called us the Research Excellence Institute in India with the citation awards, and the World and Asia University rankings, as well as QS University rankings, and the QS World University ranking by subject have also been considering VIT for some important ranking slots. We have entered within the world 500 in quite a few departments, but on the whole, we are still around 800 or so in the QS ranking. We are fast catching up. And we are also one of the Diamond Universities are rated by QS, and we are ACBSP accredited for business, and we are also ACCA accredited. BBA program has been accredited from 2017, and then we are doing well in business too. Well, coming to the School of Mechanical Engineering, VIT Vellore, it has 5 departments, 4 research centers, 4,790 students, and 10 programs and 30 plus laboratories to its credit. Some of the laboratories are coming up. As of now, functional laboratories are about 30 or so. And we have more than 210 faculty members and many funded projects. So with this thing in a nutshell, I'm going to begin about my project with SPEL, SPIC Electronics Company, which is situated in Chennai, and the websites are given like these very partners. Well, it was for a consultancy project on electronic manufacturing, assembly, and packaging of ICs. So the kind of ICs that we are talking about are kind of described in the next few slides. SVC, as you know, is an autonomous engineering college affiliated to Nine University, where I started the work and I concluded it or completed it in VIT. It's still open-ended kind of. And SPEL is an all Indian company that is totally into export market. There's something very wonderful about that place. It's all homegrown, but it's all for the outside market. So the customers of SPEL are listed here, like some prestigious companies like Pericom, Silicon Labs, then Cosmic Circuits, and Mazet, and then Bones, and Microsemi, and other companies. Well, some of the customer audits for SPEL during the time of investigation, that was say way back, say 10, 12 years back, where for Samsung, Hitachi, IBM, Sony, then Pericom, and then few other companies. Like normally we do customer audits for perception ranking, or say perception rating, or finding out new opportunities for business and then doing business with them. So like for perception's sake, like what others think about SPEL and so on, like so many things were done. Presently, some of them are happily SPEL's customers. Well, the contents of my talk today, webinar today, are going to kind of be specific about aims and goals of the project, specific goals of the project, and then it also will give you a brief about the background analysis and design 2D and then 3D modeling of ICs, finite element simulations that were kind of conducted rigorously, considering couple field analysis, and the steady state reliability and durability analysis that we have done, taking moisture attack and then the hygrothermal effect into consideration, essentially dealing with non-hermetic and then moisture-prone plastic material for encapsulation. Well, and then fatigue life analysis was done at the end in order to find out like how it would last with the Coffin-Manson equation, or the with respect to the Coffin-Manson equation or the analysis scheme. And then I'm going to kind of summarize and conclude and give an acknowledgement to a lot of people who helped this and made this happen, and a few references from my own work. Well, the aim and goal of the project, or the consultancy project with SPEL, was to create 2D and 3D models of dual and quad non-hermetic micro DLMP or micro dual leadless molded packages, and then thin quad leadless molded packages that are all used in miniaturized systems with low pin count and then low density and slightly slower speeds. So like they go into a lot of secondary and then other kinds of manufacturing initiatives. Evaluate, the second aim was to evaluate the effect of operational Joule heating and the maximum operating temperature with the hygrothermal effect involved in the packages. And the third one was to evaluate the effect of various stresses, strains, and failure criteria on the performance using an FEM software, and to corroborate with dye shear, thermal shock, and the scanning acoustic microscopy tests to check delaminations or say other kinds of thermally or say moisture resistant or hygrothermal fracture or failure. And normally scanning acoustic microscopy tests were done with in open air on the actual Chennai atmosphere. So like it also gave us some input on what would be the maximum operating temperatures and then the maximum allowance is possible as far as structural integrity or resistance of delamination was considered. Now, we had to apply hygrothermally modified failure criteria and evaluate steady state design safety. And finally, we applied the Coffin-Manson fatigue equations and evaluated hot-wet fatigue life. Well, in a nutshell, the goal is to conduct a very slightly complicated novel electro-hygrothermo-mechanical steady state and fatigue durability analysis of the designed and developed and manufactured micro DLMP and TQLMP IC packages. Well, coming to Microsystems roadmap for those who are slightly away from the subject. I mean, I don't presume that everybody is from materials engineering, reliability, and microelectronics. So the miniaturization part actually consists of string small outline packages, then quad packages with no leads, quad flat packages with no leads, and then wafer chip scale packaging, known good die packaging, and then others. And the high pin count, high speed roadmap actually is more concentrated on the BGA and the package on package, and then other kinds of system on system, and then other kinds of high density, 3D high density, and then other packages. So like when I completed the work, it was well before 2015. So this roadmap has been constructed keeping my work in mind, and in case there are stalwarts, please excuse me, because a lot of things have happened beyond 2015. So we are looking at QFNs which were beginning to be made and manufactured and then popularized and commercialized after 2005. And by 2010 or 2015, they had reached their kind of full growth and maturity. Well, and they say QFNs are not meant for decline. I don't know, like I'll take a call on it later. So coming to the device applications of micro DLMP and TQLMP ICs, the surface mount technology is kind of the place where you find lots of TQLMPs and micro DLMPs. They are used in video streaming. They are used in automobiles, biomedicals, mobiles, laptops, tablets, aerospace, and other electronic sensor and PCB applications, where lower speed, lower density, and miniaturization are the characteristics. Well, so the background of the analysis that I want to discuss today consists of certain considerations that were kind of very important before we did the work. SPEL Semiconductor Limited, the manufacturing, assembly, and testing company, sought our expertise in designing, developing, and commercializing the micro DLMP and TQLMP venture. So an agreement was signed with the project beginning by 2007 from Venkateshwara. The work was first carried out between SVC and SPEL and then completed at Ph.D. Vellore. It required a meticulous understanding of the IC designs, bill of materials, improvement over bill of materials, and the processes and then validation procedures. So in principle, we are looking at the influence of maximum operating temperature, Joule heating, I squared R losses, and these losses that cause thermal strain, which in case make the system kind of warp or twist, and warp or twist, and the thermal strains in turn cause structural deformation. So if we just do an electro-thermo-mechanical analysis, we are leaving moisture out as it's non-hermetic. Polymers, whether they're filled or not, they absorb quite a bit of moisture, especially at elevated temperatures. And all the maximum operating temperatures are well below 100 degrees Celsius, so that makes it more susceptible at elevated temperatures. So we had to do what's called a couple field analysis, which combines the analysis from different engineering disciplines that interact to solve a global engineering problem. The combination of analysis from different engineering disciplines that interact to solve a global engineering problem is defined as a couple field analysis. We had to do first in ANSYS, we had to do an electrical to thermal analysis, and then a thermal to structural analysis, and then incorporate the influence of moisture through analytical tools, and then do a complete failure analysis that are modified to accommodate the influence of moisture at elevated temperatures or any temperatures up to the MOT and beyond. So we had to choose what's called a sequential method, as the direct couple method analysis was not giving us precise results, as the whole process is sequential. Electrical, transient, then steady state situation, leading to, a lot of firm thermal strains. And then the thermal strains giving rise to what are called structural stresses and strains. And then we had to find out what was the influence of these Joule heating, or say the thermal component due to electrical heating, and the hygrothermal component on structural aspects of reliability, which would not lead to, say, delamination or any undesirable failures. Even one wire bonding, gold wire bonding goes bad, it's gone. So first, to a steady state thermal analysis, we did what's called a thermal analysis, got the job name .r thermal file out, and then temperatures were input into the structural analysis, where we got the job name .rst out. So we had to do a coupled analysis and then incorporate the effects of moisture into it. So die shear tests were conducted up to the maximum operating temperature to measure the shear strength between the silicon die and the copper lead frame. ICs were to be manufactured and encapsulations were to be molded using RTM. We did resin transfer molding at the company itself. The thermal shock test of the finished ICs was to be conducted using JEDEC, the A106B test, and modified failure analysis theories were to be applied, including the hygrothermal degradation effects, due to operation. Failure theories modified for analysis were Azzi-Sahil theory and then Sai-Wu failure theory. And we took these theories as, though these composites were filled and isotropic, they had different tensile, compressive, and shear strengths, very simple. So we thought it would be more precise to go for composite failure theories for particulate heavily filled or particulate moderately filled composite systems. So the overall steady state and fatigue reliability and durability was to be established for the packages to cover more than the warranty periods. And coming to modeling, so these were the dimensions of the ICs that we were looking at, a few millimeters, and the bill of materials consists of such a kind of a long list of lead frame, and leads being copper, palladium, or copper tin coated frames with the wire bonding done with gold, and die, and the other heart of the things being silicon or extrinsic silicon, which is P-type, N-type doped. The adhesive for lead frame and die bonding was a silver nanoparticle containing epoxy adhesive. Encapsulation was done using carbon black and fused silica particles, filled epoxy, and phenolic resin, which is a nanocomposite by present day definitions. So like we had to look at nanoscale things also. And Sumitomo molding compounds, like the two compounds are specifically given, were popularly considered, and one of them had an issue if the maximum operating temperature was quite high, and so we had to switch the maximum we had to switch the compound, the composition of the compound in order to suit the maximum operating temperature. So these are all some of the designs. So these are all some of the designs. This is a 24 pin. Though they say L, it is leadless, and then it has got a pin which doesn't protrude. So it's used only for surface mount technologies. So it's not used for any through hole soldering. So all the soldering that are done are kind of automatic, robotic. So the asymmetric design consisted of many kinds of designs, and we also had a lot of symmetric designs. And from the 4x4 mm printed circuit drawings, or wire bonding drawings, or the lead frame drawings, we had to construct the 3D drawings. And these are all some of the 3D models that we created. We deliberately created the ICs with the gold bonding die pad, die area, and the die, and then the copper lead frame, and then the pins, with and without encapsulation, in order to consider the effect of encapsulation on all the electrical, thermal, and structural properties. So that was pretty interesting, but we had to keep the encapsulation transparent with all properties intact. So the 3D model of a 64L, like you see the picture of the IC here, which is about 9 mm, and with and without encapsulations are shown here. So material properties, coming to the material properties that had to be thoroughly understood from the suppliers, or say some tests even had to be conducted at the company. So we have to look at Young's modulus, CTE, electrical resistivity, thermal conductivity, and Poisson's ratio. So when we do an electrical to thermal analysis, coupled analysis, first we have to take into account the electrical resistivity and thermal conductivity. And then when you do what is called thermal to structural analysis, we had to take into account the CTE, Young's modulus, and then the Poisson's ratio effects within maximum permissible limits. That's from MOT till the room temperature. So like we have not done any sub-zero or say freezing temperature analysis, might be worthwhile later. So these are all some of the material properties that we considered, they are given. And we used all kinds of 2-dimensional and 3-dimensional elements. And in case you are interested, you can take a look at these elements that we use for thermal analysis or electrical thermal analysis for the 2D and 3D analysis or the simulations. So these were used for 2D and then 3D analysis basically. Coming to some of the 2-dimensional results, like say, I said that we looked at micro DLMP and TQ-LMPs for their reliability first and then durability. So the meshing was kind of free meshing, like we use free meshing for that as it was much better. So this is how we get the temperature plot or Joule heating, and then maximum temperature obviously is between the copper lead frame and the die as it has been attached or adhered with a silver epoxy. So the silver epoxy is highly conducting, and then it just conducts all the heat to the die pad, and then so we were kind of happy that the maximum temperature was just below about 60 degrees Celsius. So the various maximum operating temperatures in a fully transient or a steady state analysis had to be first, I mean, the maximum operating temperatures had to be found out through simulation, as well as we could check how good the simulation was when we did the test with unencapsulated and encapsulated ICs. So sometimes we get maximum operating temperatures that are kind of threateningly close to the glass transition temperature. I'll come to that later. So coming to the coefficient of thermal expansion issue, there are methods which are kind of used for reducing the CTE mismatch between silicon, copper, then gold wire bonding, and the encapsulant material. So they all had different CTEs. So we had to do what is called a polymer underfill tactic in order to remove the CTE mismatch considerably between the chip and the substrate. Or the thin quad leadless molded packages or micro DLMP packages are very flat. I mean, they're less than 1 mm, most of them. So it was quite easy that the distance from the neutral points were very small, and then we could go in for a better CTE match. Coming to some 3-dimensional meshing results. So you see nice, good-looking, asymmetric, free-meshed, fully encapsulated and then unencapsulated IC. We went for a ball tip bonding of the gold wire with the silicon die. So when you kind of press the ball onto the substrate, then you get almost as kind of a square pattern with a bump. So like that's what we get. So like we went for a ball tip bonding. So the mesh view and the boundary conditions for the 24L TQ-LMP are given. Like first you just consider it at 25 degrees Celsius, go for the maximum operating temperature. Then you can do the analysis at maximum operating temperature or any ambience that is even in excess if you are kind of interested. So this is the picture of the micro DLMP. There was a bit of a problem with the micro DLMP, which was mostly used for, video applications. So this particular Joule 8-pin or 12-pin or 6-pin micro DLMP was only 1 or 2 millimeters or maximum 3 millimeters in dimension. And we had to use some polymers or fill polymers, and the encapsulation sometimes had to be switched to a better grade, Sumitomo grade filler, and to accommodate for the safe factor of safety between the maximum operating temperature and the lowest wet glass transition temperature. So like this is another picture. So Coming to the electric plots and then the temperature distributions, like there are a few more results that you might want to kind of check. The total deformation, interestingly, for such millimeter based ICs of say 2 mm, 4 mm, or 9 mm, or maximum 10 mm dimensions, the total deformation is about 1 or 2 or 3 or 5 microns of warping or bending, because of thermal stresses and strains that create some kind of warping. So, but this small deformation is enough to give stresses or von Mises or equivalent stresses that would be about 200 or 300 megapascals within the IC. So it's very serious. So the temperature distribution were kind of temperature distribution and then deformation simulations are shown here, where you see maximum deformation occurring in the encapsulation area, not near the pin in the encapsulation area. Like the deformation is pretty controlled here. So coming to the temperature distribution, we see for a particular IC where the maximum operating temperature is about 50 degrees Celsius, the maximum temperature is near the pin, copper lead frame, and the die attached, as I showed you earlier in the 2D analysis. So the stress intensity factors, XY shear stresses, von Mises stresses, displacement vectors, some plastic strains, stresses, and then other things could be deducted from a thermal structural analysis, which was the second coupled analysis that we did. We even focused on X, Y, and then Z component stresses. Coming to the analysis of 4 into 4 mm TQLMP at about 125 degrees Celsius for 24 hours, which is not necessary actually, but we just punished it unnecessarily to see what would happen to the reliability of the IC when you apply failure analysis. The analysis of 24L TQLMP, like that has also given us a lot of interesting results. Now, based on all these results, we had to now kind of go into some experiments, like through which most of the simulation. So we had to conduct what's called a thermal shock test, or JESD 22A106B JEDEC standard, where the IC packages are baked in an oven for 125 degrees Celsius for 24 hours. And the temperature is 5 to 260 for lead-free products. Now it's all lead-free, so we don't do with lead anymore. Like most of the plating or the other things are all done with tin and then tin compounds. So this was the kind of procedure that we adopted. If the baking temperature is kind of higher than the glass transition temperature at this extreme heat, the package tends to kind of delaminate or fail. So the influence of glass transition temperature on delaminations was pretty strong compared to many other criteria. Hygrothermal behavior. As we had already done the electrical to thermal and the thermal to structural analysis, we wanted to kind of incorporate the influence of moisture attack at room and elevated temperatures. We know that plastic packages are known for environmental attacks. They are non-hermetic and they kind of reduce their function. The mechanical properties degrade over time. Moisture plays a work at elevated temperatures in the presence of voids, defects, and in low TG plastics. So diffusion and osmotic pressure are kind of the driving mechanisms for hygrothermal attack. Evaluation methods and then surface preservation are kind of the protective or control methods. It is very important that we do that in marine, biomedical, aeronautical, dental, and then electronic and then automobile applications. Coming to the famous Shamis-Sinclair equation that could be adopted well or adapted well for linear elastic composite like a nanocomposite, which had diffuse silica, carbon, black, and phenolic and then epoxy mixed materials. So this particular formula was kind of found to be very precise in matching the simulations with the experiments. So this kind of predicts the wet TG and the dry TG. So as the increasing moisture content, as pointed out by the arrow, plays a bigger role in converting the dry TG into wet TG for any plastic material, the wet TG is found to be lower than the dry TG. So normally if you have a dry TG, that is about 120 degrees Celsius, you might often find that the wet TG is about 100, 115 degrees Celsius only. And when you consider the maximum operating temperature, where the moisture susceptibility or take-up moisture is more, we are in for slight surprises here and there, as the maximum operating temperature must be at least lower by a comfortable factor compared to the wet TG of the encapsulant material. Coming to the retention ratio that was plotted from some of the quite proven analytical equations. For the various encapsulant compounds, we find that anywhere from 110 to 130 degrees Celsius were the end. And it was not able to kind of give us a failure analysis based safety factor beyond that. So we wanted to ensure that coming to the voltage voltage requirements prescriptions by the manufacturers, or say 6 volts or 9 volts or 2 volts or 3 volts for the ICs, and the material, bill of materials and the design, we had to kind of look into certain aspects that might have a strong influence on something spilling over. Coming to the strength again, like at about 120 degrees Celsius, the difference between the tensile capacity and the shear strength, it's all gone at about 120 degrees Celsius for almost, say, some of the encapsulant materials. Coming to the other encapsulant material that we also considered, I mean, I'm sure a few other encapsulant materials were also considered, but I'm just giving you a hint of how different encapsulant materials play a big role with respect to their wet TG. With respect to their wet TG, I mean, other things being more or less equal. So as the wet TG plays a big role in choice, and then the choice of the encapsulant and the process itself with respect to the process itself compared to the MOT, or the maximum operating temperature, and the lowest wet TG, or the glass transition temperature. As it plays a big role, we have to be very careful about choosing encapsulants. Coming to the die shear test, experimental die shear test, we also had to worry about what would happen to the copper lead frame and the silicon die attached at the maximum operating temperature, or the temperature up to the maximum operating temperature. So the shear strength, a shear strength of 20 megapascals or 30 megapascals might decrease at the maximum operating temperature of, say, about 50 or 60 degrees Celsius into 5 or 10 megapascals, which may kind of make it very easy for the silicon die to shift and then kind of dislodge the wire bonding, or say any of the construction integrity, constructional integrities. So coming to a failure analysis, simple failure analysis. Coming to a simple failure analysis exercise with the die shear test for a 24 LTQLMB test. I mean, this was done for almost all the ICs, but I'm just showing a few examples of how the procedure went on. So the maximum permissible shear stress was about 21.875 MPa, or Newton per mm squared, for a shear area. And coming to the shear force of 10 kilogram force that was used, coming to a shear force of 10 kilogram force that was used, the actual shear stress was much lesser than the shear strength. So we were happy that even at MOT, or say 25 degrees Celsius, or any temperature in between, our die and the copper lead frame were absolutely safe. Coming to the generated stresses in simulation and then the actual test done, we were kind of happy. We applied the Assis-Sahil theory and then the Sai-Wu failure theory, because like the compressive failure compressive tensile and the shear strengths of the materials were different, or the encapsulants were different, and then we had to go in for directional, some of the directional properties also, as it was very thin and then it was behaving like a layer. When you apply the failure theory, the X stress or the Y stress or the X stress or the Y stress or the XY shear stress could be considered, and then the tensile, compressive, and the shear strength could be considered. The Psi-Wu failure theory actually was applied, and then the Psi-Hill failure theory was also applied. And we were pretty happy with the application of failure analysis theory after considering the moisture attack things. So when you consider the wet TG formula by Shamis and then evaluate the tensile, compressive, and the shear strength versus temperature with saturated moisture equilibrium, assuming steady state saturated moisture rate equilibrium, then we could apply the failure theory after modification and then find out whether it would be a problem at 25 degrees Celsius or 50 or 100 degrees Celsius. And that's what we did. Coming to the maximum operating temperature, it was still behaving well. And we had an equation of the left-hand side being, much less than the right-hand side. And we were absolutely convinced that it could survive the maximum operating temperature. Coming to the survivability at a peak conditioning temperature of 125 degrees Celsius, which is closer to the glass transition temperature of some of the encapsulants, there was a problem and then it failed. So there was a problem. So like the survival of it anywhere near near the glass transition temperature was a question. We also did what is called the scanning acoustic microscopy at about 50 or 100 megahertz. We did what is called a 60 or 100 megahertz scanning acoustic microscopy, considering the dimensions and the sound frequencies and attenuation patterns that were involved with the velocity, frequency, and the wavelength of the sound. So we did use about 50 megahertz or so we did 50 megahertz to 100 megahertz choice. And we could do the scanning acoustic microscopy of, with plasma cleaning or without plasma cleaning. But when we did the plasma etching or plasma cleaning of the materials, plasma etching or the plasma cleaning of the materials, we found that plasma etching or cleaning was actually better, as it did not give rise to any oxidation or contamination or any other things. And then the addition or the wettability was much better, and then it gave rise to fewer delaminations. So without plasma cleaning, it's actually, initially it was bad. I want to show you the worst case picture, to be very honest. Now, with the plasma cleaning, this was the picture before preconditioning. And once you put it in the thermal chamber with the JEDEC test prescriptions, from 125 degrees Celsius to a sudden thermal shock to 250 or 260 degrees Celsius, like it was slightly better. And then we had about let's say for a set, we had 8 failures, became 4 or 5, and so on. And at elevated temperatures, you see a movement of even the wire bonding, and then you see even a movement of wire bonding, and you see lots of die-attached problems with the copper lead frame itself. That is deliberate in order to punish it and see how far it would go, and what would be the prescription even from MOT to, say, something like the lower wet glass transition temperature. Well, there is an interesting ASTM STP D 5229 rule. Coming to almost the end of my talk. I mean, I'm very happy that despite I started a bit late, I will be finishing within time. ASTM STP D 5229M has a rule. The maximum operating temperature of the material device component should be at least 25 degrees Celsius lower than the lowest TG. normally wet TG. Dry TGs are higher, and then wet TGs are kind of lower for plastics after saturation equilibrium at least of the material. In this case, the mole compound qualifies this clause as the maximum temperature developed due to Joule heating is about 83.3 Celsius. For some of the TQLMPs, it was as high as 83. So the Joule heating was about found to give a temperature of maximum operating temperature about 83 degrees Celsius in the 64-pin TQLMP. Size plays a role, obviously, sometimes, but not in micro DLMPs, because the voltage that you have to give for a micro DLMP played a big role. Like a small 1 mm, 2 mm stuff taking 6 volts was too much for it. So electronics people kind of prescribe, but we material liability people have to worry. The wet TG of this was about 121.25 degrees Celsius. So we recommended this particular encapsulant for, TQLMP 64L IC. So we made such prescriptions, and then this is just one such an example. Fatigue durability, coming to the last part of my work. Well, coming to fatigue, this is a very interesting open-ended topic, and then I just want to leave a few loose ends free so that we think aloud about it. Fatigue is the most common failure mode in IC packaging. And IC device dissipates to the heat to its surroundings during differential thermal expansion generates stresses in the interconnecting structure. So IC device dissipates heat to its surroundings, and during operation, differential thermal expansion generates stresses. These stresses produce instantaneous elastic and plastic strains in the material joint. As the mechanical properties of material change strongly over normal temperature range of operation, the room temperature mechanical built-in stresses and that kind of result from thermal mismatch, especially with the other materials, will relax and vanish over time. That's one good and bad aspect. So cyclical plastic deformations change the grain structure or weaken the joints, and then they can lead to fatigue. The time of the joint fracture depends on relative deformation, strain, or say temperature and frequency of deformation. So a simplified Coffin-Manson relation would be number of cycles root multiplied by the relative deformation of the plastic strain, and then you can switch, will be a constant. As fatigue goes by and embrittles the structure, giving less and less plastic strain, there are a few issues. Coffin-Manson fatigue versus CTE is this taken from Rauthamala's book, the wonderful book on microsystems. He's also one of my super seniors from Indian Institute of Science. So like this is a beautiful relationship that fatigue life versus coefficient of thermal expansion is kind of plotted. Well, so we had to look at the plastic strains, total strains, and then the component for one cycling. Let us say like you just switch on, allow a PCB board or a system to arrive at the maximum operating temperature, and then after the time steady state you switch off, it's one fatigue cycling. So like every day, like if you're a kind of a hyper user, you switch on and switch off 5-6 times a day. Otherwise, some of them leave it on and then it's in a steady state for a longer time, and then you just switch off at night. So like normally, like we assume that cell phones are never switched off, like very rarely are they switched off, but laptops and desktops are switched off more often. So we had to kind of take such things into consideration. And the total strain and then the plastic strain were all calculated. And we had to kind of go back and find the weakest bimaterial interface at which delaminations occur first, and where they occur we had to check, and it was normally in the copper lead frame encapsulant pad area. Most of the preconditioning experiences have revealed that more than 90% of the failures occur in the pad area interface. The following plot, this is a Coffin-Manson fatigue graph created to predict the lifetime of IC packages investigated here. When we plot plastic strain versus the number of cycles, it's not an SN plot, it's different from an SN plot. And we find that the plastic strain severely kind of comes down even after, say, about 50, 100 cycles of normal use. Normal use is kind of 1 to 5 cycles a day. That's normal use. So we find that even after 100 cycles, the plastic strain severely is reduced because fatigue kind of normally makes a material a lot embrittled, and then it kind of sucks off a lot of plastic strain. But what happens is that when plastic strain is removed at elevated temperatures, when each time you fatigue cycle from room temperature to the elevated temperature or the maximum operating temperature, because of cycling, the moisture susceptibility increases. When moisture susceptibility occurs, it takes a bit of moisture, becomes a little more plastic again. So what I suspect is that Coffin-Manson may not be everything. We have to do plasticization because of repeated cycling and then moisture susceptibilities in the long run. And we have to check what would be the swing in plastic strain with respect to cycling. Theoretically, when all plasticity is drained out because of your Coffin-Manson relationship, which is not true. You get a life of, say, only 500 cycles. That may be about a year, but actually it is not true. We actually observed that we could have no warranty problems even after 3 or 5 years, and then it was because of the moisture susceptibility increasing with cycling from 0 to MOD. And the plastic strain kind of peeping back and forth when the cycling occurs. And it gets a bit plasticized, and then it gets fracture resistant. It becomes a bit ductile, and then it doesn't fracture anymore, like it is kind of cozy with a bit of plasticity that's normally necessary for any good survival. So we find that though we did Coffin-Manson, then like this is an open-ended question, and then I'm doing more work on this. As the plastic strain reduces, I'm going to finish in the next 1 or 2 minutes, and thank you so much. As the plastic strain reduces with cycling and only a small value of strain remains after a few tens of cycles at MOT, thereby slowly embrittling the encapsulant in the process, the overall deformation or strain, which is simulated or measured for a single steady state cycle, will be very high. With cycling, the total deformation or strain reduces and reaches a steady but low value. Reaches a steady but low value. The plot resembles an endurance SN plot for ferrous material with a limit. So like it goes on flat. If anything happens below that, it doesn't fracture. Because of severe cycling and then some more plastic strain being added in a cyclic manner, or say kind of it could be some kind of an attenuation pattern like a curve, where the plasticity is slowly removed with more and more of fatigue. Like the same moisture susceptibility is maintained, but the plastic strains are not able to kind of survive because of severe embrittling of the material as fatigue goes by. So I want to do some modeling and studies on that. Well, the fatigue life of the ICs are expected to be much higher than what we did with Coffin-Manson, which was definitely conservative. So coming to the design philosophy and pyramidal substantiation, the product we hope is reliable, and beneath that the subassemblies and the assemblies are tested the least, and beneath that the subcomponents and the components are tested less often, and the test specimens are tested more often, like wafer, then chips, then assemblies, and then motherboards, and then other kinds of motherboards, and then the sub-assemblies are tested least. And finally, we hope the product would survive better, and very few cell phones are tested. So this is called the pyramidal substantiation of survival, durability, and reliability. Summary and conclusions. Well, we did the modeling of some micro dual and then TQLMP IC packages. And we did thermomechanical analysis of IC packages after Joule heating using FEM software was carried out. We did dye shear tests, JEDEC tests, scanning acoustic microscopy tests, and hygrothermal behavior analysis and validation through failure theories for all the packages. And we also did static and fatigue design durability tests and analysis during operation at MOT and beyond. The operation of the ICs at an elevated temperature was also analyzed in order to find out where it would start failing above MOT, whether the criteria of MOT being at least about 25 degrees Celsius lower than the lowest TG or wet TG was satisfied or not, was also kind of done. Well, some of the salient milestones that the complete CAD design, FEM simulation, development, manufacturing, testing, validation, and marketing were 100% indigenous at that time. And it was a joint effort of SPCE Chennai. I happened to meet Dr. Krishnaswamy Srihari at SPCE when he paid a visit in 2007 or 8 or around that time, and we're just about to do this work. And I'm very happy that he is listening. Well, and it was a joint effort of SPCE, VIT, and SPEL. The entire IC packages produced as an outcome of the project were for foreign market with a cradle to cradle lead time of less than 5 years from development to kind of commercialization. Current work, like this is not from the SPEL work, I'm just adding a slide. I am looking at cashew nut shell liquid as a potential material for encapsulation, as it is a rat resistant, termite resistant, as it is hygrothermally very stable than some of the basic epoxies or phenolics, and it has good adhesion related characteristics, and it is easy to process with phenol formaldehyde or acid curing or alkali curing. They are bio-derived and then cost effective. They're very cost effective because a liter of cashew nut shell liquid costs you $1 or $2 in US currency, and then this shell liquid from the shell with it, from which you take the cashew nut is available in some of the cashew rich areas, and then we buy them, and we can produce a lot of products for a very cheap price, and then they can be cured at 120 or 180 degrees Celsius. Acknowledgements: my students Balaguru, Karthik, Sanjay, Dakshinamurthy, Saravanan Ram, then Selvamani, Sudhir Kumar, Hariharan, my Anna University colleague, and then Subhish Soman, whom I have to thank a lot because of the fact that he was formerly with SPEL. He is in US now, doing wonderfully well. Like, he was an excellent buddy, and he is still. And the managements of SPEL, SPC, and VIT. And I thank Professor Krishnaswamy Srihari, and then Professor Mohammed, and Professor Pollock, and others for the wonderful opportunity that they have given me today to kind of put a part of my work on the screen and sharing with the webinar. References, some of my references are given here, that were publications connected with this, or publications that are totally from this investigation with book chapters, and one ANSYS conference best paper award in multiphysics category. Well, some of the references are given here, and thank you so much. I look for your questions. Like, I just quote from Rig Veda that says, that is beautiful about convection, convection, and radiation. That one coming being was covered with void that arose through the power of heat. So, like, when we do all this fabrication and then processing and all that, we have to worry about delaminations, voids, bubbling, convection, convective problems, in bottom up to convective problems. So the Rig Veda has already some basic guidelines on that. Thank you so much.
Dr. Krishnan, thank you very much for the wonderful presentation. We have thoroughly enjoyed it, and appreciate you taking the time to deliver this presentation about your work with the company in Chennai. At this point, we would like to open it up for questions. If you have any questions, please feel free to unmute yourself and ask the question to Dr. Krishnan.
Dr. Padmanabhan.
Yes, sir.
Hello. Yeah, Raghu here. This packaging techniques you're talking of, what are the latest packaging techniques available apart from the ones which are being researched on?
Techniques are definitely in multi-layered, chip-on-chip, then system-on-system, package-on-package, and flip chip ball grid arrays, and even octa-core processors are coming into the picture. But last 2 or 3 years, I have not been seriously looking at the recent chip architectures, but I'm looking at more bio-derived encapsulant materials that can be done for encapsulation at a cheaper cost and then better properties. Because, for example, I'm looking at cashew nut shell liquid, which is rat-resistant, termite-resistant, hygrothermally more resistant than some of the difunctional or trifunctional epoxies. And that's also easily colorable or say amenable to filling or say composite fabrication. It can even be used as a protective coating, as the the ingredients like cardinol, cardol, anacardic acid, and then monophenol, and then other things. Some of them are hydrophobic for information. So we don't have to have a big headache with this moisture-prone things. Like I still have a few chips of cashew nut shell liquid cured with formaldehyde lying around in my lab, and then it has not yet turned yucky, even after say 7 or 8 years.
But this will be, how different will it be for MEMS? Like MEMS, we have three-dimensional moving pictures.
Well, I mean, I'm sorry, I'm not a MEMS guy. I'm a materials reliability guy.
Oh, okay.
So like, I'm sorry that I cannot give you a full picture now.
Okay, fine. Thank you very much.
Thank you very much, Professor.
I too would like to thank you for a wonderful presentation. I really enjoyed it. In fact, it reminds me of former days at IBM when some of these initial efforts were underway. Literally a whole building of engineers to measure material properties at exacting details and precision. A team to do all kinds of modeling with the idea that development activities at even IBM could be reduced to just doing modeling work. And it's good that now our models are becoming more and more comprehensive so that we now can, maybe build fewer parts when we try to do qualifications and things like that. And your examples are really, really great to see the progress. One thing that we learned when we were dealing with the lead-free issues and dealing it for circuit boards, large complex circuit boards, was to increase the glass transition temperature and to use materials that really brought it up above 260 degrees C. I know, working with companies like Analog Devices, they too have these same kind of issues. Issues with hydrothermal stability, issues with failure in the field, but they all persist in using the same commonly available encapsulants and molding compounds, which are low TG. Do you see a need or a trend to move that TG of the materials up?
Can you please repeat the last sentence, sir?
Do you see any benefit to working like we did with the circuit boards, to work with perhaps more expensive but higher TG materials in the epoxy molding compounds?
Yes, sir. Like I think it would be a viable option to look at some bio-derived plastics, like the badam-derived or say castor oil-derived or cashew nut shell liquid derived. Some of them are they are thermosets when you consider acid alkali or formaldehyde type of curing. And I'm particularly impressed with cashew nut shell liquid that was talking about. That gives me a thermal sealing of about 260 to 300 degrees Celsius with a TG that was more or less better than some of the entry-level difunctional epoxies. So one cost-effective initiative could be to look at bio-derived resins that can be cured or synthesized without any environmental concerns or disposal concerns or toxic concerns. That is one direction to take. And then there are other synthetic materials like polyimides or say polyamide imides and some thermoplastics that can be comfortably recycled when the life cycle is over, with a good grade of a good deal of recyclability. Of course, polyimide cannot be, but once we have other thermoplastics that have a high TG, like PPS, PPO, and the polyaramid or say polyamide type of materials with fillers and all that, I'm sure we'll be able to push the TG up to about 250 degrees Celsius, which is
cost-effective, right?
Which is not too difficult, but I'm a little worried about the cost when we look at high temperature plastics, and then I think it would be a better route to go for bio-derived resins.
Great, great. One last comment. We too looked at bioderived materials to add to resins, and at that time we were looking at lignin, which is a waste product from paper pulping. It, however, turned out to be susceptible to high temperature, and some of our materials started to smoke when they were exposed to elevated solder. But that was an early attempt to look at a huge waste material, lignin, that comes out of all paper manufacturing. Unfortunately, it wasn't suitable, but it seems that you found a suitable one. So congratulations on that. And again, thank you for a wonderful talk.
Thank you so much. Thank you so much.
Thank you very much, Dr. Pollux. Any other questions for Dr. Krishnan?
Yes, Rajesh.
Yes,
thank you so much, Dr. Krishnan, for your presentation. So you talked about pad cratering, right? So the kind of stresses that you were testing at probably might be at higher amplitude. So from experience, or from literature, we know that if the peak loads are higher, unless prevented by solder mask, you have cratering at the pads. If you are cycling at a lower load, you could expect the failure to occur in the solder or in the intermetallic. So do you think your stresses were high, especially the kind of loads or stresses that you were using?
See, the main problem is not with materials, because there is no design without materials, and then you name it, you have the material you want, provided you're willing to spend. The main problem is that the electronic prescriptions of 6 volts or 12 volts or 2 volts for a particular purpose has certain miniaturization problems, especially in the low speed, low pin count materials. So what happens is that when you reduce the size a lot, and then when you look for a cost effective, few pens, or say a few things, or a few paise, a few rupees a piece kind of thing, what happens is that if you have a 6 volt or a 8 volt or a 10 volt prescription for a small IC with a low TG encapsulant, or say other times, the thermal load will be very heavy. There must be some agreement between materials engineers, reliability engineers, then size and mechanical dimensioning or tolerancing kind of engineers, and the electronic engineers, like a concurrent approach with a house of quality. You've got to sit together and then decide what would be the size that is required. On one side, you are greedy to miniaturize with the bill of materials available. On the other side, it cannot take 6 volts or say 10 volts of the application that is necessary in order to produce a particular electronic application, because the thermal loads from Joule heating, not only Joule heating, Seebeck or Pell shear or Thomson effects are all included. I have done only, in this presentation, I have done only Joule heating. So when you do other things also, like you've got to look into the size effect, and then the latent heat, and then other kinds of specific heat or diffusivity or thermal conductivity related issues. Like this is a severely an interdisciplinary issue. Size, bill of materials, design, and then the electronic inputs that you give in order to achieve a particular function. So certain miniaturization exercises are, I would say, a pipe dream. Like if you are looking at 1 mm, 2 mm operational stability or durability for 3 to 5 years, then you got to look into cost, better bill of materials, or say the right type of voltage or current inputs to do the function, and what would be the minimum size allowable. I hope I answered your question.
Yes, you did, Dr. Krishnan. I had another supplementary question, if time allows. So, so you talked about the Coffin-Manson equation being an underestimate of the life in actual service.
I'm very happy that it is conservative.
Most of the time, in life, the damage wouldn't be happening under the same amplitude, correct? You will have a varying amplitude, and at least a small variation, systematic variation in amplitude have shown that the Coffin-Manson relationship or any other damage accumulation models actually break down when you vary the amplitude. So have you also seen, or have you also tested something where you see the breakdown of these kinds of fatigue modeling?
Well, the answer to your question is pretty simple. See, normally, like when you switch on a system with a lot of these ICs, either surface mounted or say put in PWBs or PCBs and then all that, like within half an hour or 1 hour, like you normally once you switch on a desktop, laptop or a mobile phone, you work for at least half an hour or 1 hour and you leave it on. So normally we are looking at a condition or a situation where it reaches the maximum temperature and then it hangs on there as a steady state. So as far as the thermomechanical considerations are concerned, it is a fixed amplitude worst case. Steady state is a worst case. It's a fixed amplitude worst case conditioning. So, and Coffin-Manson equation assumes some kind of a plasticity multiplied by n power 0.5, which is a constant. So for the sake of a constant, you're kind of simulating a particular thing. But in real practice, as you kind of cycle it with respect to the hydrothermal conditioning or thermomechanical conditioning, with the fixed amplitude reaching steady state and then you switching off in the night and then starting in the morning again, when such a thing happens, the moisture susceptibility of the non-hermetic plastic encapsulant would slightly increase. Though fatigue embrittles, though long cycle fatigue embrittles, the moisture susceptibility would increase and it will absorb more moisture either because of material being susceptible to moisture absorption, molecular or structure wise, and then it also differs. It also gets into what are called a micro cracking or delamination kind of a situation when these things are acceptable and then well within the limits of functioning. So because of accepting a lot of moisture and then the moisture absorption at an equilibrium or a steady state condition or a cyclic fatigue condition, the plastic strain would increase and then keep it on for a longer time. Understood?
Yes.
Yeah, this is actually the condition. So I chose Coffin-Manson so that it was all conservative and then real. As there is more reliability in Coffin-Manson, I chose it. But that need not be everything if you are looking at a real-time picture. In fatigue, what happens is that you choose Soderbergh if you're very conservative, like a stock German. But Goodman is more real. Goodman is more real. Goodman will tell you the exact picture, but Soderbergh will tell you, like, I mean, you are being deliberately 20% or 10% conservative, and that's a good thing. I mean, you will never be had by any warranty or reliability or any legal expert. That's it.
Thank you, Dr. Krishnan.
Thank you, Rajesh, and thank you, Dr. Krishnan. Dr. Vasudevan, would you like to say any words to conclude the session?
Thank you very much, Professor Padmanabhan. Great presentation. I'd like to thank Professor Muhammad for his excellent support and efforts. Thank you very much, sir.
And thanks to my darling Dean, my close friend, and then he has been a big support to me. Thanks a lot.
Thank you very much. Yeah. So I'd like to thank Dr. Krishnan again for the wonderful presentation, and definitely enjoyed it and enjoyed all the questions from our faculty colleagues and students. And I'd like to let everyone know that in a few days, we will send a recording of Professor Krishnan's presentation. This way you have access to the recording and you can share with your colleagues and students and friends. Please feel free to share the link with everyone. I'd also like to let you know that our third presentation is scheduled for next week. And as you can see on the screen, the next presentation will be by Professor Tara Dakal. Since he's teaching on Thursdays, this presentation will be on Wednesday at the same time, US time and India time. But instead of Thursday, it will be scheduled on Wednesday, and the focus will be on recent progress in thin film perovskite solar cells. And we will send you the Zoom link for the registration, just like we did for today's session. Once you receive the link, please feel free to share it with your colleagues and students, and hope to see many of you next week. And again, I'd like to thank Dean Vasudevan for his partnership and collaboration to deliver this joint webinar. I'd like to thank our Dean Krishnaswamy Srihari for joining us today and for his support of this session, and our other colleagues from VIT, Dr. Nirmala Grace and others for helping us formulate the list of speakers for this seminar. And once again, thank you, Dr. Krishnan, for your wonderful talk, and look forward to seeing everyone next week. Thank you.
Thank you, Dr. Mohammed. Thank you, Dr. Pollock, and then thank you, Dr. Krishnaswamy Srihari, and then my dear Professor Vasudevan, and all my colleagues for the wonderful opportunity. Thanks a lot. Thanks a lot.
Thank you. Thank you very much.
Thank you.
Thank you.
Thank you very much, and have a nice day. Thank you very much.
Thank you.
Thank
Bye,
you.
everyone.